Let's go. Hello and welcome back to Calculus 3. This is the last section in chapter 14, which will deal with curvature, and we will talk about tangent vector T, unit tangent vector T. We will talk about normal vectors, in particular unit principal normal vector, which can decompose into other stuff and so on. So let's take a look. It's a fairly long lesson, and I did ask you to warm up your wrists so we don't have any carpal tunnel issues. Oh, I did not connect. Yeah, perfect. Give me an hour, I'll be right with you. Curvature. You have a curve in space, x, y, z. You also have a curve on the plane, x, y. I don't care what dimensions you have, the curves will show in either of the dimension. And curvature is going to be a way to quantify how much the line bends. So these are non-straight lines. Non-straight lines have curvature at a point that you will calculate. Now, why are we talking about the point? We're talking about the point because, I'm just going to change this a little bit. Let's go like that. So what you have here for a certain length, let's say this much, you have a circle which is going to have a center somewhere below that would perfectly fit just this little piece of the line. And then you have another circle fit somewhere else and another circle. So this little curvature here, which we are going to call delta S, which is the little bit of the arc length, right? Delta S. That sits on some circle that you can draw, which will have a radius somewhere. Now, the radius doesn't have to be on axis or anywhere. It will have a radius somewhere that will trace this circle. And you are able to do this for every single piece of the line, except the straight line. Straight line, you cannot come up with a segment on the straight line that can fit the circle, because that makes no sense. So whether you are in 3D or 2D, like whatever line curve you look at, you are able to fit the circle somehow, somewhere for the small piece, and that circle is going to have a radius. So now, to define, so what's curvature? Curvature is going to be a number that quantifies how much the line bends. You all know that as you drive, for certain curves, right, you have to turn less than for others. Well, curvature is the number that will tell you how much you have to turn. So we are, nice one. So now let's define curvature. So let R describe a smooth parametricized curve. Note that the dimension is not given. So let R describe a smooth parametricized curve. If S denotes, so if S denotes arc length, and T hat, we have to talk about this creature, is R prime divided by R prime magnitude, is the unit tangent vector, the curvature is this lowercase k of S is given by change in the unit vector t in respect to S, and we have the magnitude. So it's going to end up, it's a magnitude of a vector, so it's going to end up being a number, a scalar. So we have a few things to discuss before we can go and calculate things. First off, I already mentioned R, let R be a vector. Never specify dimension. So this works in 17 dimensions if you want to think of 17-dimensional space. Great. The next one is a smooth parametricized curve. Smooth means there are no sharp corners. It's differentiable everywhere. You know that the absolute value of x is not differentiable at 0 because there is a spike, right? Absolute value of x is this V shape, and there is a spike here. It's not differentiable because derivative from the left is -1, derivative from the right is +1, and then when they meet at this one point, well, derivative is trying to take on both values. Well, you can't have a single value in space which has, single point in space which has value of -1 and the 1 at the same location. So there was no derivative in that case. So absolute value of x is differentiable everywhere except at the point. Now that curve is not smooth. It's not smooth because it's not differentiable at that spike. There are cusps as well, something like that creates another spike. Sharper than the one on the left, obviously. And then you have, you can describe, as you will see later, you can describe a curve. You can use parametric equations to describe a square or a rectangle. Well, that's not smooth either because it has those sharp corners, right? So smooth curve, if you need to write this, we're going to use this a lot, the word smooth throughout the course. The word smooth just means differentiable, differentiable everywhere. And in some sense means just no sharp corners, no spikes, none of that stuff. So that's the parametric size. Now then S is the arc length. Well, the arc length is the length of the arc on the curved line, so we understand what that is. And here we are talking now about this unit vector, unit tangent vector T. Unit tangent vector. You will be sick of this one because it's everywhere in calculations. So unit tangent vector is when you take the derivative of r and you divide it by the magnitude of derivative of r. We know that we calculate unit vectors from our first lecture this semester. We calculate unit vectors when we divide vector by its magnitude. We also know that the tangent happens when you take the derivative of the function. So if your function is the vector valued function r, which shows the position, and you take its derivative, well, you are getting your unit vector because you are dividing that vector by its magnitude. So, this vector, tangent vector, will actually carry the direction of the tangent line. Remember the last class we talked about the motion in space, and I mentioned that you can calculate the tangent line to the space curve. Well, this is going to be that vector v that you have to come up with the equation of the tangent line. So this creature is very important, and you will use this vector a lot. So make sure you remember this, or tattoo this on your arm or something. It's going to be used a lot. So now, what do I have? The last thing that we need to understand is actually the formula and what it says, which is why is this formula the one that calculates the curvature. So for that one, I'm just going to draw a two-dimensional line, so R2 case, and it should be enough for everyone to understand. Now I'm going to have a lazy bend over here, and then a sharp bend over here, let's say. That should be enough. Now, if the line is parametricized, that means it will also have a direction, right? Remember that every time you have parametric equations, they're always oriented one way or the other way. So you use for circle, cosine, then sine is counterclockwise, you use sine, then cosine is clockwise. Well, for the lines that are not circles, they either move to the left, or flow to the left, or flow to the right. It doesn't matter for us. We're just going to pick whatever. So let's have it go this way in terms of orientation. Now observe what is happening here. If I pick an arc length ds, and you pick a point somewhere on the ds, you know that the tangent vector is going to point this. So we'll call this unit vector, tangent unit vector, and it is for this point. You know what? I'm not going to call it ds. Let me put point capital A, and I'm going to call this one TA. Now, right before that one, I'll pick another one. And as you can see, this tangent vector TB at the point B did not shift that much from the other vector, right? Maybe I should change A's and B's so you have a B, because I have, yeah, let's swap. If you're using pens, it's amazing, because now your drawings are going to be terrible. I'm swapping A's and B's here. There we go. So you see that progressing from A to B, going from left to right, progressing from A to B, your tangent vector did not adjust a lot. Of course it did. It's like 15, 20 degrees over there between the two vectors. But look what happens for the tangent vectors on the same size ds, same length between A and B. Now let's call these not A and B, let's call them C and D. Your tangent vector at D should go like this, and a tangent vector at C should go like that. Now, t equals 0 to come up with A, and t equals 1 to come up with B is a length of time that you take to go from A to B. And their tangent vectors are not the same, but they have some separation. Now look here. It's almost 90 degrees, right? For the same amount of, just move a little bit forward. So this is what curvature measures, and this is how it measures it. It is how much the tangent line changes in respect to the arc length. So for the same progression in arc length, you walking on the line 1 foot or 1 millimeter or whatever, right? So you progressing 1 foot along the arc length on the bend, you see that your tangent changed a little bit or changed a lot. If the tangent vector changes a lot, it's a sharp bend. If the tangent vector doesn't change a lot, it's not a sharp. Guys, this is extremely, insanely important if you want to work as a mechanical engineer on design of roller coasters, right? You have to, marry this with physics and all other things to make sure that roller coaster actually stays where it should. But they have a lot of those sharp turns and twists and so on, and this is something that they have to know really, really well if you are to design those thrill rides. Now, that should be a booming industry, given that the tickets, like for a daily pass, like $700 or something. Do you know that the day in Disney is $900 now? Like, who's going anymore at those prices? But anyway, going back to this, you are going to, $900 for a family pass, not for one person, but it's still. When you are going at the, when you are going into a sharp bend, you see that the tangent vector changes a lot. When you go into the lazy bend, the one on the left, the tangent vector doesn't change a lot. So the formula that the curvature in respect to the arc length S is the change of the tangent vector in respect to the arc length. So you see that the sharper the turn, right, the tangent vector changes more as the arc length progresses from one point to another point. Now, I hope it's clear what curvature measures. I hope it's clear that it's just a number that you attach to a curve. The bigger the number is, the faster it turns. The lower the number is, the less it turns, which should make sense. And if you know this piece of information, you should be able to answer, what is the curvature of the straight line? The less it curves, the smaller the number. What's the curvature of the straight line? It should be common sense. 0. Straight lines do not curve. Straight lines should have curvature of 0. Now, that's just common sense with what we have seen there, because every tangent vector to the straight line is always the line. So there are no tangent vectors that would break off of the line to create any curvature. Now, this is not something that we would use to calculate things, because we do not calculate anything in terms of the arc length. We calculate things in terms of the parameter t. So now there is a one-line manipulation for you to change this formula into the formula that you will use to calculate curvature. So you are going to take your k of s, which is absolute dt, and we are using hat because it's a unit vector, right? So dt hat ds, and we are going to multiply this with 1 over dt and 1 over dt. So you are multiplying both top and the bottom of the fraction with 1 over dt. So that will create dt over dt divided by ds over dt. We still have the absolute value. And now what we know is ds dt, guys, ds dt is the velocity, right? ds dt is the velocity because you are covering distance in time. So the bottom part is the velocity, and the top part is just the derivative of the unit vector. And that creates the formula for curvature, which is given as a theorem 14.1. It gives you the formula for the curvature in terms of parameter t, which is all of your R of t's are given in terms of t's, they're not given in terms of s. So it's easy to compute. So as a formula, you guys will have this now. K of t is given as the magnitude of t hat prime, so the derivative of the unit vector, tangent unit vector, right, divided by the magnitude of r prime of t. So this is the way to compute curvature. So use this to compute curvature. Now, when you have constant curvature, like circle, then at every point of that line, curve, you will have the same curvature. If you have variable curvature, then your curvature will come out to be as a function of t, and you need to specify the point at which you want to calculate curvature. So the problem that I have up there has a variable curvature, because you see that where I have A and B has one value of the curvature which is smaller than where I have C and D, which has a larger value of curvature. So in the case of that problem, your curvature for the entire line will come out to be a function of time, and then you will plug in t equals whatever, where your interest is, and you will calculate the curvature at that point. For circle, has the same curvature everywhere, no matter where you compute, right? It will always give the same number. And we also said the straight line has zero curvature. So let's show those three cases as examples and put curvature to rest. So number one, we can also put this as a theorem, but we don't have to. Curvature of the straight line is zero, because straight lines don't curve. Very simple. But let's just, solve a problem. And it's easy to just come up with a two-dimensional problem because we're lazy. So, yes, you have y equal mx plus b, but we know that we have a multi-dimensional formula for straight lines using parametric curves. So x equals to, let's say, 3 plus 2t, and y equals negative 6t, whatever. So if you put these two together, solve each one for t and equal them, you will get y equal mx plus b of some sort. But we need this R2 line. So this is R2 line. You can convert into y equal mx plus b. This R2 line has these two formulas, and now we can immediately take this parametric set over here and write it the way we like it, which is the column vector, which we call vector valued function. So 3 plus 2t, negative 6t would be your, not r prime, sorry, your r. So when you have set of parametric equations, it is trivial to write the vector valued function because you just plug those in as components of the vector. Now, you have your vector, and you know what to do. There is the blue formula here that calculates unit tangent vector, and then there is the red formula here that will eventually calculate curvature. So, the first order of business, because both formulas use r prime, is to calculate r prime of t, which gives us 2 and negative 6. So r prime of t is 2 and negative 6, a very simple derivative. So now, we are supposed to calculate unit vector t. Unit vector t is calculated when you take vector r prime and divide by the magnitude of r prime. So vector r is 2, negative 6, and then you have that divided by the magnitude, which would be 4 plus 36. So the whole thing over here is 2, negative 6 divided by square root of 40. Now 40 is 4 root 10, so that's 2 root 10. So this is 1 and negative 3 divided by root 10. Just to simplify it a little bit, we don't care. It's just whatever it is there. Because We don't see any variables t in that vector, right? So now, if I need to calculate my curvature, what do I need? I need t prime divided by r prime. Well, t prime is 0 because there are no variables here, there's just numbers. 1 divided by root 10 is a number. Derivative of that number is 0. Derivative of the other number is 0 as well. So, if I add 0, divided by whatever the r prime magnitude was, root 40, and we get that the curvature is equal to 0, straight line. Which we knew it was straight line because we picked the straight line in our parametric equations. So we just did an example. If you want to write this in terms of a proof, instead of using particular example, you will just use x0 plus at and then y0 plus bt to write it as a proof for R2. Number 2, again, not a theorem, but you can think of it as a theorem. Curvature of a circle is constant. Yes. Because the t is a number. When you take the derivative, you will get 0. Because it's a magnitude, right? You will get a vector 0, 0. And when you take a magnitude of a 0 vector, you will get 0 as a value. That will be much clearer now when we do something that is not 0, because you will see the calculation. Earlier we had nothing other than saying derivative of 1 is 0, derivative of negative 3 is 0. But now with the circle, you know what? Let's just use general terms for a radius. Instead of doing the example, let's say radius is 3, let's just keep radius of a circle to be capital R. So we work out the problem for all circles. And then you can just replace R with whatever value you have. So say you have a circle, right, 2D, again, given parametric equations, x equals capital R cosine t, y equals capital R sine t. T goes between 0 and 2 pi to draw the full circle. Looks like there's lag. So R equals cosine t, R equals sine t. Those are my parametric equations, and t is between 0 and 2 pi. Yeah, probably projector is thinking. Come on. Oh well. Well, then the next step is to put vector r together, and vector r is going to be vector of r cosine t, comma r sine t. Now I can, no, not that one. T, y as r sine t, you can come up with the r, which is just these two. Cosine t, r sine t. Really? Then you can come up with r prime and calculate t and then calculate prime. So it's just gonna take me a few seconds to restart the. There was a issue with bandwidth, which is when all of this goes south immediately. I have to wait for the projector to cool off and all that stuff. So you have your R. R prime is individual derivatives of each one of these. R, capital R is just a number constant. You copy that when you take the derivative. So it's very fast for you guys to come up with R prime. Once you have R prime, you will divide that R prime with the magnitude of R prime. So now you have to calculate the magnitude using squares and stuff.
Yeah. Yeah, because when I was looking, if you do like r sine squared plus r cosine squared whole squared, you gotta get a radical of 1, right? Okay. Okay, wouldn't it be this over 1 then?
Yeah.
Oh, then you do t hat over the 1 again. Oh, so it just be the same thing, right?
Okay, so this is, let's see if this thing works. Yes. And we are back. Let's see how long it lasts. So r prime of t is negative r sine t positive r cosine t when you take derivatives of each one individually. And then your t hat is going to be, I'll write the formula, it's going to be r prime of t divided by the magnitude of r prime of t. So r prime of t is negative r sine t r cosine t, so that was just copy, and then that gets divided by the magnitude, which is negative r sine t everything squared plus r cosine t everything squared. Now you can probably see how quickly this can go wrong, right, in terms of calculations, if these functions are not canceling nicely. Creates a whole bunch of horrors in calculation, obviously. Concept is a joke, right? But calculations are just terrible in some case. Negative r sine t, positive r cosine t. And now what do I have? Well, negative goes away. I have r squared sine squared. So r squared sine squared t plus r squared cosine squared t. All of that under the square root. So I hope you guys see that the entire denominator is just r. You factor out r squared, and that escapes the square root, becomes an r. So now I have minus r sine t, right? And then sine squared plus cosine squared is 1, right? So I'm dividing this by r, and here is my unit tangent vector, which is simply negative sine t positive cosine t, because the r from the bottom cancels the r's on top. So there's my unit vector. Right, that's all I need. And this calculation here, going from here to there, is going to be repeated because your curvature formula is also divided by magnitude of r prime. So there's no need to redo calculation, just recycle it, right? So this calculation here gave you that the magnitude of r prime of t, and this goes for all of the problems obviously, is capital R. So that calculation, I shouldn't write this in red because that's only for this problem. Every problem has its own. Let me see. Can I change the color of this? Yes, good. So this is something that is on the side. So now when I want to calculate the curvature of t, I need the t prime magnitude divided by r prime magnitude. Now t prime is going to be derivatives of these. That's negative cosine t, negative sine t. And I need the magnitude of that divided by capital R, which is the magnitude of R. I already have that. Now the magnitude on top is the square root of these guys squared. So I have negative cosine t squared plus negative sine t squared divided by R. And the whole thing works out to be negative 1 over R. This is literally a formula for a circle. Curvature of a circle at every point on its circumference is always 1 over the radius. So if your radius is 3, it's 1/3. If your radius is 10, it's 1 over 10. So curvature of the circle of radius R is k equals 1 over R, and it is constant. So at all points on the curvature, right, is this much. The last example that we are going to cover is going to be one of the homework exercises that it's not going to have constant curvature. So let's see something beautiful. So problem number 16. R of t is given as t ln of cosine t. Now you might go, whoa, ln, hold on. We're doing derivatives, it's going to be easy and nice. You know the drill, right? Step number 1, get r prime. Step number 2, get vector t. Step number 3, get t prime, right? And then just put the formula together. Right, it's like 3 steps. Then we'll see what kind of calculations we get. So try this on your own for some time. Your exam problem on Tuesday is going to look something along 16, right?
radical states, which would then that just be C. Forget identity. You do so then secant would be your R, right? Secant would be your R, right? No, that would be your R, magnitude of R prime. That would be your secant, right? So your magnitudes would be secant, right? Okay. Yeah, T hat, but like when you're using it for the next step, right? Oh, okay. No, but the magnitude is. Yes, then it'd be secant.
Nice.
Okay.
Yes. That's why the ln is there, to make it easy. All right, so r prime of t is 1. And then you have ln, which means the argument goes in the denominator, its derivative goes on top as negative sine t. Now that simplifies into 1 comma negative tangent t. That's important. The next step is to get t hat, which is the vector, divided by the magnitude, 1 squared plus negative tangent t squared. So when you square a negative, it goes away. This becomes 1 negative tangent t divided by square root of secant squared t. 1 plus tangent square is secant square. And this is where the square root and the square cancel. So your t hat as a vector is now 1 over secant t, comma, negative tangent t over secant t. So now basic identities for trig fix a lot of this stuff. 1 over secant is just a cosine, so that's just going to be a cosine t. And tangent is sine over cosine, secant is 1 over cosine, so this works out to be negative sine t. Oh, that is so nice. So curvature of t is a t prime magnitude divided by r prime magnitude. So t prime is the derivative of what we have up there. So that's going to be negative sine t, negative cosine t, and we need magnitude of that, so we'll keep this. Divided by, and we already know that the magnitude of r prime is secant t because we calculated secant t as the magnitude of r prime earlier. So now I need the magnitude on top. So k of t is going to be, well, that's just 1, the magnitude of sine and cosine, because when you square each one of them, you get sine square plus cosine square. That's 1. Square root of 1 is 1. So square root of negative sine t squared plus, you will immediately know this is a block when you see it because it shows up a lot, divided by secant t is 1 over secant t equals to cosine t. So here it is. Curvature as a function of parameter t is cosine t. So now we see that the curvature depends on the location where you are measuring curvature. So for straight line, curvature was 0 everywhere. For a circle, curvature everywhere is 1 over radius. Now for this particular curve, whatever it is, you can go and in your graphing utility, type in the parametric curves and see what you get as a graph for this. the curvature for this particular curve is going to be given by cosine t. So now it's up to you. You want to need t equals 0. Well, curvature is 1. You say t equals pi over 2. Curvature is 0. Right, and so on. So curvature is going to be either a number, 0 or 1 over r, if it's a straight line or circle, or it's going to be a function which turns into a number when you provide location t. Now, at exams, I see a lot of times students forget to compute the curvature at the point because you focus too much on this calculation and then you forget to go back and check if the problem asked for a specific curvature. So for instance, this problem like this can state find the curvature for these at t equals pi over 4, right? So if there is this extra piece of information in the problem, well, you just spend 10 minutes cranking this. Make sure you go back into the problem and see if there is an extra piece that is actually asking you to compute curvature. Because if it's there, you still have one more step, which is curvature at pi over 4 is cosine of pi over 4, which is root 2 over 2. And that is the full credit answer, because you were asked to calculate curvature at the point, not curvature in general. So the problem can ask for a curvature in general, which cosine t would be the answer, or it could say at and give you a specific time parameter, right? So in that case, you will go and you would compute. So this concludes the first part of the lecture on curvature. The second part is on normal vectors. Let's take a short break and then we're going to have a part 2 for this lecture on the stream.